Okay, guys, so last lesson on energetics. And so what we're going to look at today is the effect of temperature on spontaneity. And so remember that for a reaction to be spontaneous, Gibbs free energy needs to be negative. And so that is what makes a reaction spontaneous. Now, let's actually backtrack a little bit and let's talk about favorable versus unfavorable situations. We've discussed this already, but let's reevaluate it. And so if we're talking about enthalpy changes, the change in enthalpy, and we have a reaction that is exothermic and a reaction that is endothermic, which of these is favorable? Remember that low is stable and high is unstable. And so stability is preferred. And so that if we have a delta H that's negative, that's favorable. And if we have a delta H that's positive, that's not favorable. And so favorable is a delta H that's negative. That's a good thing. That's what we want. So if delta H is negative, that's favorable. Now let's look at entropy. If you look at entropy and you have decreasing entropy versus increasing entropy. So here your delta S is negative, and here your delta S is positive. This is entropy on this axis now. Remember, what's favorable for entropy? Greater entropy is favorable. More entropy is favorable. The more disordered. So this is the favorable situation. And so if entropy is positive, that's favorable. So in this case, we have two favorable situations. We have favorable enthalpy and we have favorable entropy. Now look at the mathematics of what happens here. We have a negative value here minus a positive. You know, temperature is going to have an effect on it, but minus a positive. If you minus a positive, you subtract it. And so we take a negative minus a number, and we get a negative number. That's our answer, a negative value. And if our Gibbs free energy is negative, then we're spontaneous. We're favorable and we're favorable. Favorable here equals negative Gibbs free energy, which equals spontaneous. So when are we favorable? When enthalpy is negative and entropy is positive. If you have those situations, you will always be spontaneous. So negative, so delta H is negative, delta S is positive. This is always spontaneous in that situation. Negative enthalpy, positive entropy, is the reaction will always be spontaneous. Now, what if we flip that? What if we make the enthalpy positive and the entropy negative? So remember, enthalpy being positive, that's not favorable. And entropy being negative, that's becoming more ordered, that's not favorable. If both of these situations are not favorable, we will never be spontaneous. Never spontaneous. Now let's look at the mathematics just to double check. Remember, we need a delta G value that's negative. If H is positive, and we're going to subtract from it S, which is negative, we're going to a subtraction of a negative means an addition. So a positive plus a number equals a positive number. So you would have a delta G that's always going to be positive with that scenario because of the mathematics. All right, now, those are the two easy ones. Always spontaneous, never spontaneous. What about if we have opposing favorabilities? What if we have a situation where the enthalpy has a negative enthalpy and the entropy is also negative? So in this case, this is favorable and this is not favorable. What happens there? Or what if we have a reaction where we have enthalpy that's positive and we have an entropy that's positive? Here we would have non-favorable, not favorable, and then this would be favorable. What happens? Is the reaction spontaneous? Is the reaction not spontaneous? In these two situations, the spontaneity of the reaction depends on the temperature. That's what happens. It's a temperature-dependent reaction in regards to spontaneity. So let's evaluate that. All right, so let's evaluate a reaction. Let's say that we have an enthalpy that's negative 400, and we have a change in entropy that's negative 2. Remember, entropy is usually pretty small compared to the enthalpy. And let's evaluate this reaction. Let's evaluate it at 100 Kelvin, and let's also evaluate it at 300 Kelvin. All right, so let's plug in. So negative 400 minus the temperature of 100 Kelvin times negative 2. And then we'll do negative 400 minus 300 Kelvin times negative 2. So if you look at this situation and you do your mathematics, 100 times 2, or negative 2, would be negative 200. So negative 400 minus negative 200 means positive plus 200. So that's going to be an answer of negative 200. Now, down here, 300 times negative 2 is going to be negative 600. So negative 400 minus negative 600 is plus 600. So that's equal to positive 200. All right, so we have different Gibbs free energies, different values of Gibbs free energies. In this case, we had a negative 200. That's spontaneous. In this case, we had a positive 200. That's not spontaneous. And so how did temperature affect the spontaneity? And so in this case, at the low temperature, relatively speaking, this is relative speaking, at the relatively speaking lower temperature, we had spontaneity. As the temperature increased, we changed from spontaneous to not spontaneous. So if you have a situation where the enthalpy and the entropy are negative, then you are spontaneous at low temperatures. Relatively speaking, low temperature. Now you actually have to determine what that relative speaking that temperature is based on the different H's and the different S's. Different reactions have different relative temperatures to consider. All right, so let's look at the other situation. Let's say we have a situation where the enthalpy is positive, which is that's not favorable, and the entropy is negative. Is also positive. When that is favorable, what happens? So again, let's evaluate this. So we have delta G equals delta H minus T delta S. Okay, so let's give an enthalpy change of positive 300, and let's give an entropy change of positive 2. Let's evaluate this at 100 Kelvin and at 300 Kelvin. So let's do those two evaluations. And so at 100 Kelvin, the enthalpy change is positive 300 minus the temperature of 100 times the entropy, which is 2. So that's going to be positive 300 minus 200 equals positive 100. So it's positive, that's not spontaneous. Okay, let's reevaluate at 300 K. So delta H would be 300 still, minus a new temp of 300 times 2. So that's positive 300 minus 600 gives you negative 300. Now that is spontaneous because our sign is negative. So the evaluation once again, we are spontaneous here at 300 and we are not spontaneous here at 100. So relatively speaking, if our both values are positive, we were spontaneous at high temperature. We became, as the temperature went up, the spontaneity flipped from not spontaneous to spontaneous. So the information contained here, you need to know. You either need to know it, memorize it, or be able to logically figure it out during a question. It doesn't really matter how you do it, but just be able to determine the spontaneity versus the non-spontaneity. If you want to memorize it, a long time ago I learned how to do this, and I just kind of made up a mnemonic for myself. And so negative to positive, we are getting better, if you will, and so that's a good thing, and so that was always spontaneous. Positive to negative is going bad, and so that was never spontaneous. If they were both negative, that'd be spontaneous at low temperatures because they're both low. And if they're both positive, that would be spontaneous at high temperatures because they're both high. And so that was how I did it. You learn how you want to as far as memorization is concerned. I do want to give you one little more thing here. At what temperature does a reaction change from spontaneous to not spontaneous? If you want to determine that, then what you want to do with your equation is you want to set G, delta G equal to 0, because that's when it shifts from negative to positive, is at 0. So set G equal to 0, plug in your enthalpy, plug in your entropy, and solve for T, and that tells you the Kelvin temperature at which a reaction will flip from spontaneous to not spontaneous, or vice versa, depending on which way you're shifting your temperature. Okay? That is it, guys. We are done with energetics.